Hello everyone. From today, I'm starting July as the month of DP. Every single day, I'll be uploading one problem in which I'll be solving a new DP problem. Okay, they'll be either taken from SPOJ or they'll be taken from code forces or from different websites. They'll be solved using different techniques, but they all will be DP. And as we cover DP, in one of the lectures, I'll also cover as to how do we actually go about solving DP. What is the thought process behind solving DP? So, but we start with certain examples, and today, our question is from code from SPOJ, which is RPLB Blueberries. Essentially, the I won't go into the text of it. I won't go too deep into the text of this, but what this problem says is that this is an array that's given to you, and you have to select certain elements from it, okay, and sum up the elements, okay, in a way that the total sum cannot exceed 100 in this example. Okay, so 100 is the maximum that you can go to. Okay, so this is first constraint. The second constraint is that if you have picked an element I, you cannot pick I plus 1th element. Okay, so if I have picked 50, I cannot pick 10. And if I have picked 10, it means that I would not have picked 50, and I cannot pick 20 as well. Okay, so this is the constraint that we'll be living with. And under such scenarios, we have to tell what is the maximum sum that we can generate. So there is this entire story in the question that you can go through, that I'll be skipping for my video, but this is the gist of the question. Okay, cool. So let us see how do we solve this question. So let us first try to make a graph. So the first example is 50, 10, 20, 30, 40. So it says 5, 10, okay, and this is 50, 10, 20, 30, and 40. So let me just confirm it once again. 50, 10, 20, 30, 40. Yes, that's correct. So let us see what happens. So suppose I start by choosing this first element 50. So where can my graph lead to? I cannot choose 10, so I can probably take 20. Okay, and if I have taken 20, it means I cannot go further and take 40 because the sum will exceed 100. Okay, so this graph ends here. Okay, now if so, this is the first thing. Okay, and with 50 in place, I cannot take 10. I can choose not to take 20, so I could have probably taken 30. I could have probably taken 40. Who knows, right? In similar fashion, I could have actually started with 10. I would not have taken 50 in place. With 10 in place, I could have taken 30, and because 30 is there, I cannot choose 40 now. But I could have also taken 40, right? So there is no foundation. And in fact, I could have chosen not to take 10 as well. So this graph would so as big the array, this graph would actually continue, right? So now see, if I have not, if assume that I had not taken either 50 or 20 for a moment, let us assume that, okay, and the graph is actually sufficiently big. So what would have happened that after 20, okay, or let's say our limit wasn't 100, let's say our limit was some 200, okay, after 20 I could have chosen 40, right? I could have chosen 40, and let's say there are some numbers 60 and 80, and so after choosing 40 I could have actually chosen 80 here. And if you look at this graph here, there's a 40 node here, after which the graph would actually repeat, right? So this graph, the whole subtree would actually be similar to this subtree, right? So in similar ways, sorry in similar ways, the subtree that starts at 30 would actually be similar to subtree that starts here. And in similar ways, we also see a 40 node here, right? So what we are actually observing is that there are multiple there are multiple similar or exactly same graph which is being created. So in a normal scenario, we can do a brute force. We can try every single combination which is possible in this given array. But what that would mean is that it would be an exponential complexity. The problem would take just for a sufficiently large array, it might just take infinite time to solve. So that is obviously not the right way to solve the problem, right? Given we have only 1 second, we have only 1 second to solve it. Now these repeating arrays, right? These repeating graphs, the graph that we see here, the graph that we see here, the graph that we see here, and the graph that we would have seen here are sufficient example, are sufficient instances or evidences for us to consider dynamic programming. Because if we can remember what happens when we are at 40, we would never need to solve that problem again. We can just simply remember that and use that information, right? So this is exactly what we are going to do uh, while solving this problem. So let us see how can we go ahead and solve this. So instead of immediately divulging into the code, what I'll be doing is I'll be developing some intuition, some pseudo algorithms. So we now know for sure that it is a dynamic programming problem. So let us see how to go about and solving this problem. So I'll write this example again. So it says 5 and 100 is the maximum. It says 50, 10, 20, 30, 40. So 50, 10, 20, 30, and 40. Okay, now see, there are multiple things. So one of the ways in which I solve a DP problem is to see how many things are variable here. The first guy which is a variable is weight, right? So based on the current weight, we have a decision to make whether we can choose the next element or not, right? So weight is definitely a factor contributing to the state of the DP. The other factor is, sorry, the weight sum. I would call this as a weight sum, okay, and current weight, right? So this is the another factor, right? Wherein for the current weight that you are at, okay, if there is a weight sum that you have achieved, how far or how can you execute further, right? So these are the two variables that are going to impact the DP, right? There is no third thing. So there is no third variable in our problem that is going to impact the equation or the impact the code that we are going to write. Okay, so this is how actually I understand what is going to be the state, what is going to be the dimension of the DP. So because there are two variables, it is going to be a two-dimensional DP. Okay. Okay. Now that we know this is a two-dimensional DP, let us take our variables. Let us define our variable. So I will define a variable called I, which is the current index, right? Then I'll declare a variable called weight, which is the sum of weights until I. Okay, and I'll also let's have a different let's have a static variable called total, which is actually 100 in this case, maximum sum. So this doesn't change, right? This doesn't change. So what will happen is that at any point of time, at any index I, there are certain choices that I can make. So the first choice is if weight, okay. So if weight plus array of I, and I call this thing as array. This thing here is called an array. If this exceeds total, right? If this exceeds total, then you definitely cannot pick this array, this element, right? So if this if the weight that we have until now plus the current weight actually exceeds the total that you can achieve, then you cannot pick the current weight. So what we'll do in this condition? So let us write this condition here. So in this case, what we'll say is we'll actually have to find out the solution for the current weight that we have, right? Because we are not able to pick this current weight, we will go to I plus 1, and obviously total will remain total, right? So this is what we'll have to solve for. Okay, cool. So now that we know what do we solve for when we are exceeding the total weight with the current index, let us move to the scenario wherein we actually know that the weight plus the weight of current index does not exceed total. So what happens in that case? So let's say, oops, I'm sorry for this. Maybe selected the wrong pen here. Okay, in this case, we have two choices to make. Either we can, so in this else case here, right? In this else case, essentially this is weight plus weight of current element is smaller than equals to total, right? This is what we are dealing with right now. So in this scenario, we have two choices to make. The first scenario is A. So let's say some int A equals to weight plus array of I, okay, comma I plus 2 comma total. So this is one. Let me write the another thing and I'll come to the explanation part of it. The second is weight comma I plus 1 comma total, right? So what happened in first scenario? What happened here? So the point that we were trying to make is in this first scenario here, we considered the current weight, which means we took a decision that we are going to take the element at current index I. Now this I plus 2 signifies that because we have chosen I, we cannot choose I plus 1. So we'll have to go to I plus 2 and total remains total, okay? And the value B here, the value B is here signifies that we have taken a decision not to consider the element at index number I, which means that I can actually now choose the element which is present at I plus 1 and total remains total, right? Total doesn't changes. Now that we have two numbers A and B, the choice will be the one which actually maximizes my weight, right? So this is essentially the pseudocode. This is essentially the core logic of our DP here. So you have two variables, weight, which is the sum of weights until I, and the current index, right? And there are two conditions that gets created here. First is when you just cannot choose the element at index I, and the second condition wherein you have a choice whether you want to choose the element at index I or not, right? So the case wherein you just cannot choose, which is this case here, this is a very simple case because you simply have to move forward, you add nothing to the weight. But in the scenario wherein you actually have a choice to choose this element at index number I, you have two variables that gets created and you have to choose the maximum that the maximum of the two elements A and B. Now let us see how we actually write this code. Okay, now that we have the whole pseudo code in place, let us see how we actually go about writing this code. So I will be writing this code here, but I will definitely not be submitting it. You can do the submissions. Okay, so first thing first, let us create a variable called db. Okay, and how do we create this variable? So now we saw that our dp is of two dimensions, right? There are two variables that are impacting this question, right? So the dp is going to be of two dimension, which means it is going to be a two-dimensional array. So for this question, let me take a sufficiently large number. Okay, so I have declared my variable dp. Now let us declare something called a function. Okay, so let me say our recursive function in this case is maximize berries, right? And what are the variables that this function is taking? The first variable that we saw was the integer, the index at which we are currently functioning, right? The second variable is the weight that we have achieved until now, again an integer. For third and fourth variable that are going to be static, I am going to take total, which is the maximum, and I am also going to take a vector of int, okay, a vector of int, and this is going to be passed as a reference so that I avoid doing copies of array which can slow down my program, okay. Now in DP it is because this is also a recursion, right? Because this is also a recursion, it is very important to have base conditions in place. If you don't have base condition, it is going to be an infinite recursion and definitely your program will not work. So first thing first, let us write some base conditions. If I is greater than equals to array dot size, which means obviously I cannot go beyond the length of the array, right? So in this case, all you have to do is simply return the weight that you have, because you cannot there are no choices to make, right? Your I has exceeded the limits of the array and there are no further choices to make. So we simply return whatever weight we have until now. The other condition is what if we have actually calculated, right? And now this is where you will see the importance of having two-dimensional DPs in place. Now for ith index and for the weight that we have accumulated until now, right? If we have already calculated, so let's say if the value at these indexes is not equals to -1, it means that we have already calculated this particular sub problem, and we are going to simply return dp of I comma weight. Now one very important thing to understand at this point of time is that at a particular index I, so let's say if I talk about this index 20, right, this index 20 here, it can have different weights, until now, right? So maybe 50 was chosen and then 20 was chosen, so 70 was a possibility and 0 was also a possibility, because it is entirely possible that I do not choose 50 and I do not choose 10 as well. So this ith index can have two sums, so 0 1 2, right? So this second index can have a value at 70 and this second index can have a value at 0 as well, right? In similar ways, different indexes can have combination of different sums, which is where we are saying that if for an ith index here, if for an ith index we have already if for an ith index and the sum of weight that we have achieved until now, if we have already calculated that sub problem, we don't really need to calculate it further and we simply return. Now then comes the core logic of our DB, which is if the weight that we have accumulated until now plus the weight of current array, if it is actually smaller than, or I would say total, if it is smaller than equals to total, then this is a good sign for us. Now we have two variables like we said earlier, a, which is maximize berries, and what we pass here is, in the first condition we actually choose to take the current element at the element at index number I. So I becomes I plus 2 because we cannot choose I plus 1. Weight becomes weight plus weight of array, okay, and the last two variables remain as is, which is array and total. It doesn't change. The second variable that we will get is int b, wherein we make a choice to not choose the current variable. So this becomes maximize berries I plus 1, because we have not chosen the current element. Weight, and again weight because we have not chosen the current element, so the weight doesn't changes and the last two element simply tags along. And what you will have to do is at this point of time, dp of I comma weight is equals to maximum of a comma b, right? And in the last scenario that we have here, dp of I comma weight equals to maximize berries, right? And we don't have a choice. We cannot pick the current element because it increases the weight to from the limit of the total that we can achieve, right? So we don't have a choice. So we make it I plus 1 comma weight because we cannot choose the current element, and the last two parameters just tag along, right? So yeah, so this is the core logic, and end of the day what we do is we simply return dp of I comma weight that we calculated either here or here, right? So this is the core function that we have. Finally, what we also need to do is we also need to in so let's say we have a main function, right, that is going to call this. I'm skipping the part wherein you are supposed to take input of array and all, but one interesting thing that you have to ensure is that you have to set all the elements of dp array to -1, okay, and size of dp. So this is how you do it, and it is important to set it to -1 because we are making a comparison to -1 here. -1 is going to be our identifier of whether we have solved this a problem or not, right? And finally, the answer is going to be maximize berries, and what you're going to pass is, so you are at index number 0, your current weight that you have achieved is 0, and the array is array, and total is total. So yes, this is about the problem. We have solved it using recursion, and we actually saw how to come up to a decision of what is the index, right? What is the index of the dimensionality? What is the index of the array, or what is the dimensionality of the array that you are going to build upon? So for me, the simple rule of thumb is the dimensionality of the array is equal to the number of changing variables, right? Okay, cool. So this is about the episode 0 of our July month. We have solved our first DP question. I hope that you have understood it. I am also hopeful that you will go and try the solution yourself. You will not copy the code directly from here. If you have any problems, if you have any comments or suggestion, please write it in the comment. I'll be more than happy to see them. I'll be more than happy to see your feedback. And I really look forward to continuing this journey of July with DP. Thank you so much. Please like, share, and subscribe.